Okay, so in the previous two videos, we reviewed some terms about redox chemistry, and I just realized I'm not sure if people watch these videos in the order that I placed them on Blackboard, but anyway, that's what I mean whenever I mean in the previous two videos. But if you watched the two videos where we review redox reactions and then how to balance half reactions, then we haven't really discussed the electrochem part of this chapter, and that is where we are starting now. So first we talk about electrical current. So the way that you can think about electrical current is that it's like water flowing downhill. So here we have a mountain, and you see water flowing down some sort of river, creek, and electrons can act the same way. So they flow through a conductor, and they're flowing in response to an electric potential. And an electric potential is something positive. So, we've learned, hopefully you learned in Chem 1, how negative is attracted to positive. So that's what happens here. Your electrons are attracted to that potential, which is the positive, so they flow that way. So the same way that the water is flowing down, these are flowing towards positive. So it's in response, for the water flowing, it's because of gravity, right? It's going from higher to lower. But for us, for these electrons, it's because of the electrical potential difference. So it starts off from somewhere negative and it's flowing towards the positive. So electric current is the amount of electric charge that passes a point in a given period of time. So it can be either electrons flowing through a wire or ions flowing through a solution. Electrochem is the study of these redox reactions that we've been discussing that can produce or that require an electric current. So electric current is those electrons flowing from a negative to a more positive potential. And anytime you convert this chemical reaction, or this chemical energy, from this flow of electrons to electrical energy, this happens in an electrochemical cell, which makes sense, right? Electro and chemical. So we have two types of cells. We have voltaic cells, which are whenever you have spontaneous redox reactions. So we know spontaneous reactions in general do not require any outside input. They will happen on their own. Versus non-spontaneous redox reactions, they can be made into one of these cells to generate electrical energy, but you actually have to put in energy first because they're non-spontaneous. So those are the two different ones. And first we are going to be looking at a galvanic cell or voltaic cell, which whatever you want to call it, they're synonyms. So a spontaneous reaction, in order to just look at these cells in general. So regardless of what type of cell it is, these are electrochemical cells, and we have to keep our oxidation and reduction half reactions separate. We call these separate cells half cells. So remember we talked about half reactions, it's the same idea. So we have a half oxidation cell and we have a half reduction cell. So our electrons will flow through a wire above these two, they're typically solutions, but you will also need ion flow through these solutions as well. Overall, this will make a circuit. So you will have a full circuit around, so it's closed off. You need a conductive solid electrode in order to allow these electrons to be transferred. So you need some sort of metal or some sort of graphite that will allow these, little electrons to flow. Remember that image where they were flowing? You just need something that will conduct that. And you also need an ion exchange between these two half cells. So remember we said it's like a circuit, meaning you need it to be like closed off. So it also requires your ions to be exchanged between these two half cells. Here we have a galvanic cell, meaning that it's a spontaneous reaction that we have depicted here. Now I'm going to point out what everything is, and then I'll explain what's going on. So we have a salt bridge made out of sodium nitrate. We have two pieces of foil. One is copper foil, the other is silver foil. We have some sort of metal that allows for electrons to flow, as stated right here, and electrons are flowing this way. We have two solutions. We have a 1 molar solution of copper 2 nitrate, and then we have a 1 molar solution of silver nitrate. So basically those are the main components of everything here. Now let's take a look at what's going on. So on one of these beakers, right, because they're beakers that we have pictured here, in one of these beakers is our oxidation half cell, and in the other beaker is our reduction half cell. So you can tell which one is which based off of where electrons are flowing. So anywhere where electrons are flowing away from, remember oil rig, oxidation is losing. So on this side we have our oxidation half cell. On this side we have our reduction half cell because electrons are going towards it, so it's gaining. And remember, electrons are flowing here. So our silver cathode is gaining our electrons while our copper anode is losing our electrons. So we're going to discuss what anode and cathode are in a second, but for right now let's just look at it in terms of electrons and atoms and ions. So once your copper loses the electrons that start to flow up here, what happens is that it'll turn into an ion. Once it's an ion, it'll go into solution. So instead of being copper solid, which is like that, right here on this little foil, it turns into copper ion, copper 2 ion. And then for our silver, what happens is that whenever electrons come into it through the circuit, through the wire, it will be leached out of solution and turned into a solid. So you see how it's going back into being a solid. So instead of being, silver ion, it'll be Ag solid. So that's what's going on with those. Now what about nitrate and our sodium? So whenever this silver is being leached out of solution back to being a solid, you're losing positive charge from that ion. So to counteract that and to balance the charge, some of this sodium will just go into solution. So it'll be traveling into there. That's why it's made out of both of these. And then for the other side, we will have an increase in copper ion. So if you have that increase in copper ion, that means you're going to have more positive charge, right? Because it's positive 2. So to counteract that, you need to balance it with a negative ion, so an anion. So that's where this nitrate comes into play, and it starts flowing into there. So overall, you have two things occurring, remember, and they're happening separately. You have oxidation occurring on this half cell. You have reduction occurring in this half cell. So oxidation, and I'm getting ahead of myself, but oxidation occurs at the anode. Reduction occurs at the cathode. And then you can see how it's a complete circuit, like it's completely connected through the solution, through the salt bridge, through the anode and cathode, and then the wire that's allowing the flow of electrons. So definitely, if you learn all the terminology, you can connect it to images like this, and it'll make it easier for you to like analyze the situation. So this is why I said I was giving it away, because I wanted to wait to kind of summarize it all. But we're gonna discuss the electrodes a little bit more. So we know we have two electrodes. One is an anode, one is a cathode. Anode is where oxidation occurs. So for the previous example, it was where the copper was. And then for the cathode, it was where the silver was. So just right off the bat, let's talk about an acronym that'll help you remember this. So fat cat. And I don't know the credits to this beautiful fat cat, but I found this on Google and I was like, oh my god, this is perfect because I love cats and it's funny and it's a giant cat. So this stands for from anode to cathode. So the electrons are traveling from the anode to the cathode. So at the anode, you have oxidation occurring because it's losing those electrons and they're traveling to the cathode. So at your anode, your anions will be attracted to it. So that's why you saw an influx of NO3 minus nitrate. It will be connected to the positive end of a battery in an electrolytic cell. That's not the one we were discussing, but if once we get there, you'll see what we mean by that. And then for cathode, it's where reduction is occurring. Cations are attracted to it. That's why sodium was being produced and put into solution there. It will be connected to a negative end in an electrolytic cell, which is a different type of cell. So here's another image is showing you the same exact thing we discussed, but I like this one because you can kind of see like at the atomic level. So here we have a different anode, it's zinc solid. So you can see how as it's losing electrons, right, the electrons are flowing out into the wire up here, and then the zinc is like, oh my god, what do I do? So it goes into solution as an ion, zinc 2+ ion, and the electrons are given off as a product. Now from there, electrons are flowing, they actually power that. Since it's a circuit, it's a closed circuit, they power that, but they keep flowing and they reach the cathode. So your cathode in this case is copper solid. And here at the like atomic level, you can see that it's starting off in solution, and as soon as it gains those electrons, it's like, okay, now I can be a solid, and it's happy. So that solid copper collects on this cathode, and then in order to balance these out, you need these ions. So you have more positive forming here, more positive ion forming here, so you need that anion in the salt bridge, and then you have more positive ion, so cation, being leached out of solution and turning into a solid, so you need more positive flowing in there to balance out the charges. So we can quantify the current that we've been discussing and place like a unit on it, and that unit is amps. So all I really want you to know here is that it has to do with current. It measures the number of electrons that flow through the system per second. And we know that 1 amp of current is 1 coulomb of charge. We can actually quantify in terms of electrons also, which I think is kind of cool, but we're not going to do any calculations related to that. Electrode surface area dictates the number of electrons that can flow. So if you have a bigger electrode, remember we had those little pieces of foil that we were discussing on the diagram. If you have a bigger one, then you would have the possibility of more electrons flowing. Okay, so we discussed current And what an amp is. An amp is the unit for current. Current is the amount of electrons that will flow through a system. Voltage, on the other hand, has to do with the difference in potential energy. So remember at the very beginning, I keep going back to that image, or I keep referencing that image where we had the electrons flowing right that way. So pretend there's little electrons, and they flow from a negative to a positive. So that difference, right, in the negative and the positive always has to do with potential. So the difference in potential energy between the reactants and products in a chemical system is the potential difference, and we measure this with a unit of volts. So voltage has to do with how much energy you need to drive electrons through a circuit. So if it has a big difference, you need more voltage to drive those electrons through. And we actually have a force that we can describe this like pushing electrons. So the amount of force pushing the electrons through the wire is called specifically electromotive force, EMF.